Hey everybody, this is Starlight here. Today I'm going to be going through a problem from the Cracking the Coding Interview book by Gail McDowell. So the problem I'm going over is on page 136, and this is the 6th edition, 8.11. So the problem is, given an infinite number of quarters, dimes, nickels, and pennies, write code to calculate the number of ways of representing n cents. Okay, so I wrote the program in C++, and I'm going to go through this algorithm with you guys. So the program is pretty simple. I just have a main and in my recursive function, all coins. So in order to get the number of coins, n, I specify n as change, and I use a recursive function to subtract the denomination every time until we get less than or equal to 0. We can stop once we've reached less than 0. And if it is 0, we can add that to our vector, which contains the different combinations of coins. This is a vector of strings, and each string that I have will include the denominations that make up change. Okay, let me go through this with you guys. Okay, so in my main, I prompted the user for the amount of change we should calculate. Let's keep things simple and put 10. Okay. Okay, we're going to enter the recursive function, and so change is how much, it's 10. Vector is going to hold the different string combinations, and string is going to be the different denominations that make up change. So we're going to add to it every time we subtract a denomination. Letter is going to be the single denomination that we add to the string. Initially, they're both going to be empty. So when we add an empty string to another, it's still empty. All right. So in the beginning, our change is 10, so we do not add anything to the vector. Now we're going to start adding coins to the vector, or I should say to the string s, which is going to hold the different combinations. So 25 is bigger than 10, so we're not going to add that. 10 is equal to 10, so this is going to go in. So this is pretty self-explanatory, I think. You add the coins that are less than the change, right? If you can subtract it, then do so. All right, I'm going to explain this next. Previous coin is greater than or equal to 10. All right, so why do I have that? Let me write a recursive tree to make this clear. So we start off with 10 cents, and in our first recursive call, we subtract 10 from change, and we add a dime. So D stands for dime right here, and we add the letter D to our string, and since a dime is 10 cents, we're going to add that to our vector and return. We return, and once we return, so this dotted line right here represents returning back to the function that called our recursive function. So change is back to 10, as you can see right here. And right now, previous coin is equal to 25, but watch what happens when we enter the next recursive function. Alright, so previous coin is equal to 5 now. And this is significant because it's going to prevent the program from calling any functions that came before 5. Alright, this is going to be a little clearer later on. Okay, so we add another nickel. And 2 nickels is equal to 10 cents, so we're going to add that to our vector and return. We completed that, and I believe we returned to the calling function. So now, in this stage, in this level, change is equal to 5. We've only added 1 nickel so far. And we're going to add pennies from now on. So we're going to keep adding pennies until we reach 0. Finally, we have added 5 pennies, so we can add that sum to the vector. All right. Okay. Okay, after I've returned from this function, our change is equal to 10 again. And this is where it's important. This is where we're going to demonstrate why previous coin, this condition is so important. So now we're adding pennies one at a time. So we're adding pennies one at a time. So we've added 1 penny. Now notice what happens if previous coin, this did not exist, previous coin greater than or equal to 5, this was not here. Since change is 9, and that's greater or equal to 5, our program would think, hey, look, a nickel can go into the amount of change we have left. And so they would go down that route and add a nickel and eventually add 4 pennies. So that would be a nickel and 5 pennies. But you can see that that would be a problem because we have already added a nickel and 5 pennies to get 10 right here. So that's why we add this extra condition here to prevent it from traversing or adding coins that have been already added. In this case, we have already added all the different combinations involving higher denominations like nickel and dime. So we do not want to go back and add those in. So from now on, we're just going to stick to adding pennies. So so now change is 8. And remember, if this condition weren't here, we would call all coins and add n to our string, which we don't want because we've already done that in this path right here. So just for the sake of showing you guys the result, I'll complete this. So we got 6, 5, 4, let's count down, 3, 2, 1, and there we go. We're going to add our final combination. Moment of truth. Yes, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I think we've gone over all the combinations. We can return from everything. There you go. And the program has ended. So the tricky part for me was kind of figuring out this previous coin, and I hope you guys understand it by now. If you didn't, feel free to comment below, and I'll try to answer any questions you have. Alright, hope you guys learned something, and have fun experimenting. Okay, see you guys later. Bye.